There is a specific kind of silence that you can only find when you look up. Imagine standing in a wide open field on a perfectly clear night. You tilt your head back and your eyes adjust to the darkness. Slowly the light of the stars begins to pierce through the black curtain of the sky. At first you see 10 stars, then 100, then thousands. They look like diamond dust scattered across a table of black velvet. It is beautiful, certainly. But if you look long enough, and if you let your mind wander far enough that beauty transforms into something else, it becomes a feeling of overwhelming smallness. In that moment you are standing on a tiny rock spinning around a burning ball of gas floating in an endless ocean of emptiness. The silence of the universe is not just a lack of noise, it is a heavy presence. It is a silence that has lasted for billions of years. It is a silence that asks a question. Are we the only ones listening? For most of human history, we filled this silence with stories. We created gods, monsters, and myths to explain the lights in the sky. But as we grew older as a species, we replaced the myths with mathematics. We stopped guessing and started calculating. We built telescopes to see further and computers to think faster. We developed a new language to understand the unknown, a language called probability. Probability is a strange tool. It does not tell you what is happening. It tells you what might happen. It is the science of perhaps the study of the maybe. It is how we measure luck, risk, and the future. When you toss a coin, probability tells you there is a 50% chance it will land on heads. It does not promise heads, but it gives you a framework to understand the outcome. In the world of astrophysics, probability is our flashlight in the dark. We use it to guess how many stars have planets, how many planets have water, and how many of those wet worlds might hold life. Usually the numbers we come up with are very small. They are tiny fractions, numbers with many zeros after the decimal point. These small numbers are comforting. They tell us that life is rare, that we are special, and that the silence out there is normal because there is no one else to make a noise. But recently the math has started to change. The numbers are shifting. And out of the sea of calculations, one number has risen to the surface, and it is a number that is too large to ignore and too heavy to carry lightly. 40%. This is not just a number on a page. In the context of the universe, 40% is a monster. It is not a rare chance, it is almost a coin flip. Imagine walking into a dark room. You know there is a chance someone else is in there with you. If the chance is 1%, you might feel a little nervous, but you would probably walk in. If the chance is 40%, you stop at the door. You hold your breath, you listen for the sound of breathing. 40% means that for every 10 stars you see, 4 of them might be hiding something profound. This number 40% refers to the likelihood that red dwarf stars, the most common stars in our galaxy, harbour Earth-sized planets in their habitable zones. This means billions of planets could potentially support life. When you digest this fact, the night sky changes. It is no longer empty. It feels crowded. The silence stops feeling peaceful and starts feeling like someone is holding their breath, waiting for us to notice them. The number casts a shadow over our understanding of reality. It suggests that life is not a miracle. It is a standard feature of the universe. However, numbers are silent. They do not speak unless someone gives them a voice. They remain ink on paper until a human being dares to interpret them. In the rigid, careful world of academic science, very few people are willing to shout about aliens. It is a taboo subject. It is the third rail of astronomy. Touch it, and your career might die. Most scientists prefer to stay safe. They talk about microbial life or atmospheric signatures. They use cautious words. They look at the 40% and say, that is an interesting statistic. But there is one man who looks at the 40% and sees a revolution. His name is Avi Loeb. Avi Loeb is not a conspiracy theorist living in a basement. He does not wear a tinfoil hat. He is a man of immense stature in the scientific world. He served as the chair of the astronomy department at Harvard University, one of the most prestigious positions a scientist can hold. He has published hundreds of papers. He understands the physics of black holes and the birth of the early universe better than almost anyone alive. He is a man of logic, data, and rigorous proof. And yet Avi Loeb stands apart. Where his colleagues see only rocks and ice floating in space, Loeb sees possibilities that make others uncomfortable. He looks at the data without the filter of fear. He argues that if the math says life is common, we should act like it is common. We should not be searching for bacteria on a distant rock. We should be looking for the wreckage of civilizations. We should be looking for trash, for probes, for technology. Loeb represents a bridge between the cold, hard facts of science and the wild imagination of science fiction. He is a controversial figure because he breaks the unwritten rule of astronomy. Do not claim it is aliens until you have no other choice. Loeb flips this rule. He asks why not aliens? If the probability is 40%, why are we so afraid to admit that we might have company? To understand the weight of this, you have to look at the man himself. He's not loud or aggressive, but he is stubborn. He has the quiet confidence of a man who has done the math and trusts the result even if the result is terrifying. He describes himself as a farm boy who just happens to look at the stars, but in the eyes of the scientific community, he is a troublemaker. He is walking a very fine line. On one side is his reputation as a brilliant Harvard professor. On the other side is the ridicule that comes with hunting for extraterrestrials. Most people would stay on the safe side, but Avi Loeb has decided to walk straight into the shadow. He believes that the silence of the universe is an illusion. He believes that the number that haunting 40% is trying to tell us something. He believes that evidence has already passed through our solar system right under our noses, and we missed it because we were too afraid to look. When you combine the terrifying scale of the universe, the heavy probability of 40%, and the relentless curiosity of a man like Avi Loeb, you get a story that is no longer just about numbers. It becomes a detective story. The universe is the crime scene, the 40% is the clue that something happened here, and Avi Loeb is the detective walking into the darkroom, flashlight in hand, ready to see what is hiding in the corner. As we stand here looking up at the night sky, the stars do not look different than they did yesterday. They still twinkle. The darkness is still cold. But once you know the number, and once you meet the man who takes that number seriously, you cannot help but feel a change. You are no longer just looking at lights in the sky, you are looking at a neighborhood, and the lights are on. The question is no longer, are we alone? The question is, when will the doorbell ring? Or perhaps more frighteningly, has it already rung and we were just too deaf to hear it? This is the reality of the shadow. It is the space between what we know and what we are afraid to admit. It is where the math meets the madness, and that is exactly where Avi Loeb has decided to set up camp. To understand our place in the cosmos, we must first learn how to measure it. When we look up at the night sky, we usually categorize things by how bright they are, or how far away they are. But Avi Loeb proposes a different kind of ruler, a conceptual yardstick that measures something far more profound, the capacity of a civilization to affect its environment. This is the essence of the Loeb scale. It is a mistake to think of aliens merely as little green men or monsters. Instead, we should think of them in terms of energy and impact. The Loeb scale moves us away from science fiction fantasy and toward a structured way of judging what we might find. It asks a simple question. Is this object passive or is it active? Does it follow the wind or does it create the wind? At the very bottom of this ladder we find rank 0. This represents the purely natural world. Rank 0 is the baseline of the universe. It includes inert rocks, comets, asteroids, and simple microbial life that does not alter its environment on a planetary scale. If we find a bacterium on Mars that is just sitting there surviving but not building, it is rank 0. When the scientific community insisted that Oumuamua was just a nitrogen iceberg or a dust bunny, they were arguing that it was a rank 0 object. It implies a universe where physics rules alone without the interference of intelligence. As we climb the scale, we reach the levels of early intelligence. These are civilizations that can use tools and harvest energy from their home planet. This is where humanity currently resides. We are not yet masters of our solar system, but we are no longer just natural. We emit radio waves, we have changed the chemical composition of our atmosphere, and we have sent small metal boxes like the Voyager probes into the dark. However, in the grand scheme of the Loeb scale, we are still in the lower numbers. We are noisy, but we are fragile. Moving higher past the middle ranks, we enter the realm of what physicists often call stellar engineers. These are the civilizations that have graduated from burning dead plants' fossil fuels to harvesting the power of stars. A civilization at this level, perhaps rank 5 or 6, would not just live on a planet. They would manage their entire solar system. They might build structure around their star to capture all its light, utilizing energy outputs of 10 to the power of 26 watts. If we spotted a star that was flickering in an unnatural pattern, it might not be a natural phenomenon, but the shadow of a massive solar power plant built by a rank 6 civilization. Then we reach the summit, rank 10. This is the level that Avi Loeb describes as the class capable of cosmic creation. A rank 10. Civilization has mastered physics so completely that they are indistinguishable from gods. They do not just live in the universe, they can arguably make one. Loeb suggests that a sufficiently advanced civilization could create a baby universe in a laboratory using quantum tunneling. If a civilization can concentrate enough energy, perhaps 10 to the power of 70 joules, into a small enough space, they could spark a new Big Bang. This is the philosophical peak of the scale. It suggests that our own universe might not be a random accident of nature, but a science fair project created by a rank 10 intelligence. The philosophical significance of assigning these numbers is profound. It humbles us. It forces us to realize that humanity is not the main character of the cosmic story. We are barely teenagers who have just found the keys to the cell, but more importantly, it removes the fear of the unknown. By assigning a number to the alien, we turn the unknown into data. It is no longer magic, it is just a higher rank of physics. However, how do we move an object from rank 0, a rock, to rank 10, a god? How do we decide what is true when the evidence is blurry? This brings us to the second pillar of our investigation, the subtle beauty of Bayesian probability. In school, we are often taught frequentist statistics, the idea that probability is the frequency of an event happening over many repeated trials, like flipping a coin 100 times. But when it comes to aliens, we cannot flip the coin 100 times. We only have one universe. We only have one Oumuamua. Bayesian probability is different. It is the mathematics of belief. It is not about being right or wrong instantly. It is about updating your confidence as you get new clues. Imagine you are standing in a completely dark room. You cannot see anything. Your prior belief is that the room is empty. This is your starting point. Suddenly you hear a soft breathing sound. Your brain instantly performs a Bayesian calculation. You combine your prior belief, empty room, with new data sound. Your posterior belief shifts. There is now a 30% chance someone is there. Then your eyes begin to adjust to the darkness. This is exactly what science does. We build better telescopes to let our eyes adjust. You see a vague outline in the corner. It looks like a person. Now you update your belief again. The probability jumps to 80%. Finally, you turn on a flashlight, new decisive data. You see it is just a coat rack. Your belief drops to 0%. This process, constantly updating what we think based on what we see, is how we must approach the search for extraterrestrial life. When Oumuamua appeared, the prior belief of most astronomers was that it must be a rock because we had never seen anything else. Their probability for aliens was near 0, but Loeb applied Bayesian logic. He looked at the data. The object was shiny, it had a strange shape, and most importantly, it pushed itself away from the sun without a tail. A rigid thinker says, it's a rock because rocks are common. A Bayesian thinker says, rocks are common, but rocks do not accelerate like that. Therefore, the probability that this is artificial has increased. The beauty of this mathematical approach is that it allows us to be open-minded without being foolish. It allows a scientist to say, I am not sure, but the evidence has shifted the needle. It treats beliefs not as stone monuments, but as living things that adapt to the light. Just as our eyes adapt to the darkroom to reveal the shapes hidden within, Bayesian probability allows our minds to adapt to the vast darkness of space, helping us distinguish between a simple asteroid and the passing shadow of a rank 10 civilization. The silence of the solar system is not empty, it is waiting. When Oumuamua crossed the invisible line into our neighborhood, it did not behave like the visitors we know. To understand why this object terrified and fascinated scientists, we must look closely at the 3 specific signatures it left behind, clues that tell a story of impossible cold and strange chemistry. The first anomaly, waking up too early, in the textbook definition of a comet activity, is dictated by the warmth of the sun. Usually a comet is a dirty snowball. As it falls toward the center of the solar system, it remains asleep, a frozen rock, until it crosses the orbit of Mars or gets even closer to Earth. Only then does the heat become intense enough to melt water ice, creating the famous tail. But Oumuamua refused to follow this schedule. It began breathing venting gas and pushing itself forward when it was still very far away. Specifically, it became active at a distance of about 2.9 astronomical units. To visualize this, imagine the distance from the Earth to the Sun. Now multiply that by nearly 3. This places the object far out in the cold belt between Mars and Jupiter. At this distance, the Sun is not a roaring furnace, it is merely a bright, distant lantern. It is far too cold for water ice to turn into gas. If Oumuamua were a standard comet made of water, it should have remained a dead, silent stone. The fact that it woke up here tells us something profound about its heart. It suggests that the ice buried inside it was not water, but something much more volatile, substances that boil at extremely low temperatures. This implies a hyper-volatile surface reacting to the faintest touch of solar warmth, like a creature that wakes at the snap of a twig rather than a shout. It was shedding weight and pushing itself not with the heavy steam of water, but with the subtle invisible breath of gases that usually remain frozen solid. The second anomaly, a chemistry of deep cold, when astronomers looked at the light reflecting off this gas, expecting to see the chemical signature of water, they found something else entirely. This brings us to the ratio of carbon dioxide and carbon monoxide to water. To understand why this matters, we must travel back in time long before Oumuamua was a rock to the place where it was born. We have to imagine a molecular cloud. Picture a vast dark nursery in the galaxy. These are not white fluffy clouds like those on Earth. They are colossal titans of dust and gas spanning light years glowing with strange dark colours. Inside these clouds it is one of the coldest places in the universe. These are cosmic chemical reactors. In this deep freeze atoms of carbon and oxygen drift through the void until they meet a grain of dust. They stick to it and layer by layer they build up an icy coating. Because it is so cold in these stellar nurseries, water freezes instantly and hard. But carbon monoxide and carbon dioxide behave differently. They require even colder temperatures to freeze. The chemical makeup of Oumuamua showed a massive abundance of these carbon-based gases and very little water. This is a dry composition. This ratio acts like a thermometer frozen in time. It tells us that Oumuamua was likely formed in the outer edges of a planetary system, or perhaps in a molecular cloud that was exceptionally cold, far colder than the environment that birthed our own solar system. It is a relic from a place where water was scarce, or where the star was too dim to ever melt the carbon ice. It is a shard of ice that remembers a darkness deeper than anything we experience near our sun. The third anomaly, the smoke without the fire. The most baffling anomaly, however, requires us to look at the surface of the object itself. As instruments analysed the faint light coming from Oumuamua, they detected the spectral signature of nickel on the surface, but strangely there was no iron. In the natural world of astrophysics, this is incredibly disturbing. Nickel and iron are like cosmic twins. They are forged together in the hearts of dying stars. They travel together in asteroids. They are found together in the meteors that fall to Earth. To find nickel without iron is almost unheard of in nature. Imagine you are hiking through a pristine, untouched rainforest. The air is fresh, the trees are ancient, and there is no sign of civilization for thousands of miles. Suddenly you smell the distinct acrid scent of factory smoke, sulfur, and burning metal. You look around, but there is no factory, no fire, no humans, just the trees. That is the feeling astronomers got when they saw the nickel. It is the smoke of a factory that shouldn't exist. There is a potential natural explanation, but it is violent. It is possible that Oumuamua has been travelling through the void for so long, perhaps billions of years, that it has been battered by cosmic rays and dust. This constant bombardment acts like a sandblaster. Over eons, this space weathering might have vaporized the iron or buried it, leaving the nickel exposed on the surface in a way that looks artificial to our eyes. Alternatively, the nickel could be gas escaping from the interior, but again, why only nickel? Usually if a rock is melting, everything melts together. The isolation of this specific element suggests a refining process, a separation of materials that nature rarely performs so cleanly. The synthesis of the strange. When you combine these three things, the picture becomes blurry. We have an object that wakes up when it should be asleep, the distance anomaly. It is made of the wrong kind of ice, suggesting it was born in a cryogenically frozen nursery far darker than our own, the chemical ratio. And finally its skin is coated in a metal that stands alone, separated from its twin like a refined alloy, the nickel anomaly. It is a rock that acts like a rocket. It is a comet that looks like an asteroid. It is a messenger that speaks in a language of chemistry that our solar system does not speak. It forces us to ask, is this a freak accident of nature, a 1 in a trillion roll of the cosmic dice? Or is the separation of these elements the specific choice of volatile fuel and the pure metallic coating evidence of design? As Oumuamua accelerated away, leaving these questions unanswered, it did not offer a solution. It only offered the data raw and confusing, leaving us to stare at the numbers and wonder if we were looking at a stone or a machine drifting silently through the night. When we look at the night sky, we are accustomed to a certain cosmic order. Planets march in predictable orbits governed by the heavy hand of the sun's gravity. Comets, the wild wanderers of the solar system, announce their presence with brilliant tails of gas and dust burning away as they approach the heat of the star. But as we track the interloper Oumuamua, we encountered a profound silence that defied these rules. We moved from the mystery of its shape to the even deeper mystery of its movement. This brings us to the fourth great anomaly, the non-gravitational acceleration deficit. To understand why this is so strange, we must first appreciate the simple laws of motion. In the vacuum of space, the primary force acting on any object is gravity. Newton's laws tell us that if we know the mass of the sun and the speed of the object, we can predict exactly where it will be at any given second. It is a clockwork universe. However, as Oumuamua tumbled past the sun, it began to deviate from this celestial schedule. The object was moving faster than gravity alone could explain. It was being pushed. In the world of comets, this is actually quite common. As a comet heats up, ice on its surface turns instantly into gas shooting out in jets. This acts exactly like a rocket thruster. The gas shoots one way and the comet is pushed the other. This is called the rocket effect. But here lies the ghost in the machine. Oumuamua had no tail. Deep telescopic searches looked for carbon gases, water vapor or dust clouds, the exhaust of this natural engine. They found nothing. There was no coma, no haze, and no visible outgassing. Imagine seeing a sailboat moving across a perfectly calm lake. There is no wind, no engine sound, and no ripples in the water. Yet the boat continues to accelerate, cutting through the glass-like surface. This was the haunting reality of Oumuamua. It was a ghost ship, in the truest sense drifting through the ocean of night, propelled by a force we could not see and could not easily explain with the standard model of cometary physics. The acceleration was smooth and continuous, a gentle push that defied the violent, messy nature of typical comets. This leads us to a poetic consideration of physics, the nature of momentum and light. We often think of light merely as something that allows us to see, a tool for illumination. But in the language of the cosmos, light is also a physical presence. It carries weight. Light is composed of photons, tiny packets of energy that have no mass but possess momentum. When these photons strike a surface, they transfer that momentum like billions of invisible raindrops falling on an umbrella. If you stand in the sun, you feel warmth, but you do not feel a push. The pressure of sunlight is incredibly weak, roughly equivalent to the weight of a single piece of paper resting on your hand. However, in the frictionless void of space where there is no air resistance to hold you back, this tiny pressure can become a powerful engine. Over days and weeks, the relentless bombardment of photons can push an object, increasing its speed significantly. This physical reality invites us to reconsider the ghost ship. If the object was not pushing itself with gas jets, perhaps it was being pushed by the sun itself. This is the physics behind the concept of a light sail. For sunlight to push an object effectively, the object must be incredibly thin and lightweight, acting like a giant kite catching the solar wind. If Oumuamua was indeed being accelerated by solar radiation pressure, it suggests a geometry far more extreme than a simple rock. It implies a structure that is thin, broad, and capable of harvesting the momentum of light, a capability that nature rarely produces in such a refined way. While the movement of the object puzzled astronomers, the way it interacted with light revealed the fifth anomaly: the extreme negative polarization of dust and surface reflection. Polarization refers to the orientation of light waves as they bounce off a surface. When sunlight hits an object, the way it reflects tells us about the texture and composition of that surface. Is it smooth like a mirror? Is it rough like sandpaper? Is it covered in fine powder? Most objects in our solar system, specifically asteroids and comets, reflect light in a specific way known as positive polarization at certain angles. Oumuamua, however, showed a deep extreme negative polarization. In simple terms, this means the object absorbed and scattered light in a manner that suggests a very peculiar surface texture. It was not just dark, it was confusingly dark. This optical behavior hints at a surface that is incredibly porous or fluffy, somewhat like the structure of a loosely packed dust bunny under a bed, or perhaps a lattice-like material that traps light rather than reflecting it cleanly. This observation deepens the mystery of the unseen. We have an object that is accelerating as if it is light and thin, yet its surface interacts with light as if it is complex and deep. If we combine these two anomalies, the picture becomes surreal. We are looking at an entity that moves without a visible engine, gliding on the breath of the sun, covered in a material that swallows light in a way that implies a structure unlike the solid rocks we find in the asteroid belt. The anomaly of negative polarization essentially tells us that the skin of this visitor has been weathered by millions of years of interstellar travel bombarded by cosmic rays until it became a dark reddish crust. But beneath that crust, or perhaps because of it, the object behaves differently than anything born from our own sun. It brings to mind a traveller wrapping themselves in a dark cloak to survive a long winter. The surface is ancient, battered and strange designed, or evolved to endure the harsh radiation of deep space. The lack of a dust tail, the absence of visible debris, coupled with the weird way light bounces off the surface, suggests that Oumuamua did not shed its skin like a comet, it held itself together. In the end, the unseen motions of Oumuamua challenge our intuition. We expect heavy things to move sluggishly and light things to blow away. Here we had a massive football field-sized object moving with the agility of a feather, pushed by the silent pressure of light hidden behind a dark, light-absorbing veil. It moved through our solar system not like a dumb rock tumbling downhill, but like a vessel navigating a current, obeying laws of physics that apply to everything yet utilizing them in a way that seemed almost deliberate. The ghost ship did not just drift, it sailed. The architecture of trajectory. When we move beyond the physical shape of the object and look strictly at how it moved, the mystery deepens significantly. If the shape of Oumuamua was odd, its movement was practically impossible to explain using standard geology. The trajectory, the path it cut through the blackness of space, tells a story that is far more compelling than a simple rock tumbling through the void. This brings us to the 6th and 7th anomalies, which suggest that the object was not just falling but perhaps was being steered. Anomaly 6, the galactic parking spot. To understand why the arrival of this object was so strange, we first have to look at where it came from, or rather, how it was moving before it ever saw our sun. In the vastness of our Milky Way galaxy, everything is moving. Stars orbit the galactic center, gas clouds drift and planets spin. It is a chaotic highway of traffic. However, astronomers have a concept called the local standard of rest. Imagine a crowded room where everyone is walking in different directions. If you average out the speed and direction of every single person, you can find a theoretical still point. The local standard of rest is that still point for our neighborhood in the galaxy. It is the average velocity of all the stars near us. Oumuamua was doing something statistically incredible. It was sitting at that exact still point. Before our solar system's gravity grabbed it, Oumuamua was essentially motionless relative to the local standard of rest. It was not speeding toward us like a bullet. It was floating like a buoy in the ocean. It was the solar system that ran into it. We slammed into this object as we orbited the galaxy. Why is this suspicious? Because the odds of a rock randomly having that exact velocity zero motion relative to the local average are roughly 1 in 500. Most comets or asteroids ejected from other star systems would retain the speed of their parent star. They should be zooming past at high speeds relative to the galactic average. Instead, Oumuamua was waiting. It was perfectly parked in a way that allowed our star system to intercept it. If you were designing a probe to sit in space and wait for a star system to pass by so you could scan it, this is exactly how you would position it. It suggests a kind of galactic ambush, or a listening post waiting for a ship to sail into its waters. Anomaly 7, the push without a rocket once. Oumuamua entered our system and began to loop around the sun. The second movement anomaly occurred. This is arguably the most famous piece of evidence in the debate. According to the laws of physics, specifically the laws of gravity laid down by Isaac Newton, we can predict exactly where an object should go. If you throw a rock, gravity curves its path. We calculated the path for Oumuamua based on the gravity of the sun and the planets. But Oumuamua refused to follow the line. As it moved away from the sun, the object accelerated. It was moving faster than gravity alone could explain. In scientific terms, this is called non-gravitational acceleration. Now, this happens with comets all the time. When a comet gets close to the sun, the heat melts its ice. The ice turns into gas and shoots out of the surface in jets. This is the rocket effect. The gas shoots one way and the rock is pushed the other way. If Oumuamua was a comet, this extra speed would be normal. However, Oumuamua had no tail. We looked with our most powerful telescopes. There was no cloud of gas, there was no dust, there was no water vapor. We saw nothing that looked like a rocket exhaust. This created a massive contradiction. For a rock of that size to be pushed that hard by gas, it would need to shed about 10% of its total mass. That is a massive amount of material. It would have created a bright visible tail that would have been impossible to miss. Yet the space around the object was completely clean. Furthermore, the spin of the object did not change. Usually when a comet shoots out gas jets, the force is uneven, causing the comet to spin faster or slower, eventually tearing it apart. Oumuamua's spin remained steady. So we are left with a puzzle. Something pushed the object away from the sun. It was a smooth, continuous force. The force declined exactly in proportion to the inverse square of the distance from the sun. This specific mathematical decline is the key. The only natural force we know of that pushes away from the sun and fades exactly that way is sunlight itself. But sunlight is very weak. To be pushed by sunlight, an object must be incredibly lightweight and thin like a sail. A thick rock cannot be pushed by light, a thin manufactured sheet can. The tourist and the harbour. When we combine these two anomalies, the static starting position and the mysterious push away from the sun, we move from dry data into the realm of philosophy and intent. We must pause to consider the difference between a coincidence and a plan. If you walk into a forest and see an oddly shaped rock, you assume it is nature. But if you walk into a forest and see a rock that is perfectly flat, shaped like a disc, sitting exactly on the path, and it begins to slide away from you as you approach, you assume it is a machine. Let us use the metaphor of a grand tour. Imagine an interstellar civilization that wants to map the galaxy. They do not know exactly where life exists, so they place buoys or sensors in the galactic parking lots, the local standard of rest. These sensors sit quietly saving energy, waiting for a star system to pass by. As our solar system, the Sun, and its planets sweeps through this region, the sensor activates. It falls towards the Sun, using the star's gravity to gain speed. This is a maneuver we humans use with our own satellites. We call it a slingshot. The object dives past Earth. It does not crash, it does not stay. It simply observes. It passes within a distance that, astronomically speaking, is a hair's breadth from our planet. As it rounds the Sun and begins to leave, it deploys a mechanism, perhaps a light sail, to harness the pressure of the Sun's radiation. This gives it the extra push it needs to escape our gravity and return to the darkness, perhaps beaming its data back to a distant home. In this scenario, the object acts like a sophisticated tourist or an anthropologist. It treats the planets like ports of call. It visits the harbour of Earth, records the local culture, our radio waves and atmosphere, and then catches the wind, sunlight to sail on to the next destination. Conclusion: randomness or architecture. The skeptics argue that this is all just a series of wild coincidences. They say it was a nitrogen iceberg or a dust bunny or a hydrogen rock. Things we have never actually seen in science but invented just to explain this object without using the word aliens. But the architecture of the trajectory suggests purpose. Nature is rarely so precise. Nature is messy. Nature does not typically create objects that wait in the galactic rest frame, dive past the only habitable planet in the system, and then silently accelerate away without leaving a trace of exhaust. The path of Oumuamua was elegant, it was efficient. It maximized the ability to scan the system while minimizing energy use. It moved less like a tumbling stone and more like a ship under command. And as it fades into the distance, never to return, we are left with the unsettling realization that we may have been watched by a traveler who found us interesting but not interesting enough to stop. The atmosphere inside the observatory had shifted. For weeks, the air had been filled with the frantic energy of discovery, the clicking of keyboards, the shouts of astronomers sharing data, the smell of stale coffee. But now, a heavy, suffocating quiet had settled over the room. It was the silence of people waiting for a storm they could not see. We were approaching Anomaly 8. Dr. Aris stood before the main wall of monitors. His face was pale, illuminated only by the harsh glow of the orbital trajectory models. On the screen, a bright yellow circle represented the Sun. A small blue dot was Earth. And then there was the red line, the path of the visitor. The red line was diving straight toward the yellow circle. "It is too perfect," Aris whispered. He took off his glasses and rubbed the bridge of his nose, a gesture of pure exhaustion. In all of history, the odds of this happening by accident are 1 in billions. He was talking about the alignment. In orbital mechanics, we have a term called solar conjunction. This happens when a planet or an object moves behind the Sun from the perspective of Earth. Imagine you're trying to watch a car driving on a distant road, but suddenly it drives behind a giant blinding searchlight. You cannot see the car anymore. The light washes everything out. The radio signals get lost in the noise of the star. Usually this is just a routine annoyance for space agencies. When Mars goes behind the Sun, we simply stop talking to the rovers for a few weeks. We wait. But this was different. The visitor was not just passing behind the Sun, it was hitting its perihelion, its closest point to the star, at the exact same moment it entered solar conjunction. Look at the timing. Sarah, the lead dynamicist, pointed at the numbers scrolling on her tablet. The object will reach its maximum speed of 87 kilometers per second at the precise moment it vanishes from our view. It is timing its sprint for the moment the cameras go blind. I looked at the simulation. The geometry was terrifyingly elegant. The object would dive into the Sun's gravity well, accelerating violently. At the peak of that speed, when the G-forces were highest and the heat was enough to melt lead, Earth would be perfectly positioned on the opposite side. For 14 hours we would be blind. It is the ultimate hiding spot, I said, my voice sounding small in the large room. If you wanted to do something you did not want the humans to see, this is where you would do it. Aris nodded slowly. The silence within the light. That is what the poets would call it. We are scared of the dark, but we should be scared of the light. The sun is the loudest thing in the solar system. It screams in radio waves, it roars in radiation. Anything happening behind that roar is invisible to us. This realization brought a new kind of fear. Until now, we had treated the visitor like a rock or maybe a derelict ship drifting on the currents of gravity, but this maneuver suggested intent. It suggested a pilot, or an artificial intelligence that knew exactly where we were and exactly what our blind spots were. What happens in the dark? Sarah asked. She wasn't looking at the data anymore. She was looking out the window at the twilight sky. A maneuver, Aris speculated. A course correction. Think about it. If they fire their engines now while we can see them, we can calculate their new path. We can figure out where they are going. We can prepare. He walked over to the whiteboard and drew a crude diagram. But, he continued, if they fire their engines while they are behind the sun, we see nothing. They enter the blind spot on one trajectory, and they exit on a completely different one. They could change their inclination. They could slow down to enter Earth's orbit. They could speed up to leave the system entirely. By the time they emerge from the glare, it will be too late for us to react. We called it the magic trick. Every magician knows that the secret to a disappearance is distraction. You create a flash of light, a puff of smoke, and while the audience is blinking, you make the move. The sun was their flash of light. As the countdown to conjunction approached, the tension became physical. The telemetry data on the main screen began to flicker. The signal strength bar, usually a solid green, started to jump to yellow, then red. The sun's massive corona was beginning to interfere with the radio waves reflecting off the object. Signal degradation at 40%, a technician announced. Noise levels rising, we are losing the lock. We were watching a ghost fade away. I tried to imagine what it was like on the surface of that object. It was diving into a furnace. The sunlight there would be thousands of times brighter than on Earth. If it was a machine, its heat shields must be glowing cherry red. If there were beings inside, surely they could not survive the radiation unless they were feeding on it. That was the other theory floating around the room, though no one wanted to write it down in an official report. What if the jump wasn't just a change of direction? What if it was a refueling stop? The object had been cold and silent for centuries. Now it was dipping into the greatest energy source for light years around. 10 minutes to loss of signal, the voice announced. The room went completely still. We were witnessing a paradox. The object was about to be bathed in the most intense light possible, yet to us it was vanishing into total darkness. It feels like it is laughing at us, Sarah whispered. It knows we are watching. It waited until we were all looking, and now it pulls the curtain. 5 minutes. The data stream became garbage. Numbers turned into random symbols. The velocity readouts spiked to impossible figures, 1 million kilometers per second, then dropped to 0. The sun's interference was washing out the radar returns. Aris stood up. He smoothed his jacket, trying to maintain the composure of a scientist, but I saw his hands shaking. He knew that when that object came out from behind the sun, if it came out, the world might have changed. 2 minutes. Background noises extremely. Dream. I stared at the big screen. The red line touched the edge of the yellow circle. There is a psychological weight to this, Aris said softly to me. We rely on our eyes. We rely on our data. When those are taken away, we are just cavemen afraid of the thunder. We are not scientists right now. We are just people waiting for the monster to come out from behind the tree. 1 minute. The static on the speakers grew loud, a harsh hissing sound like heavy rain on a tin roof. That was the sound of the sun. It was the sound of the shield being raised. 30 seconds. I held my breath. I wondered if at this very second, behind the curtain of fire, thrusters were igniting. I wondered if giant solar sails were unfolding to catch the photon wind. I wondered if the object was changing shape, shedding its rocky shell to reveal something shining and metallic underneath. 10 seconds. 5, 4, 3, 2, 1. Loss of signal, the technician said. Contact lost. The screens went black, save for the angry swirling image of the sun. The red line was gone. The room did not exhale. The silence that followed was heavier than before. Now the clock started. 14 hours. 14 hours of guessing. 14 hours of the entire human race holding its breath, waiting to see what would emerge from the fire. We had lost sight of the visitor, but the terrifying part was the certainty, the absolute gut-wrenching certainty that it had not lost sight of us. It was hidden, it was energized, and it was making its move. To understand why we are trembling with anticipation and perhaps a little fear at the arrival of 3 Atlas, we must look back. We must turn the pages of our history books to a chapter that is stained with the tears of astronomers. We must talk about the ghost. We must talk about Oumuamua. It happened in the autumn of 2017. It was a time when humanity felt confident in its understanding of the solar system. We had categorized the asteroids. We had tracked the comets. We thought we knew the traffic rules of our celestial neighborhood. Then on October the 19th, the Pan-STARRS telescope in Hawaii spotted a faint point of light. At first, it seemed like nothing special, just another rock tumbling through the dark. But as the computers crunched the numbers, the alarms began to ring silently in the minds of scientists around the world. This object was not behaving. It was not circling the sun like a well-behaved planet or asteroid. It was moving too fast. It was diving into our system from above the plane of the planets, piercing through our neighborhood at a speed of nearly 87 kilometers per second relative to the sun. It was not falling into the gravity. It was escaping it. It had come from the deep void between the stars, and it was leaving just as quickly. It was the very first interstellar visitor we had ever seen. We named it Oumuamua. In the Hawaiian language, it means a messenger from afar arriving first. It was a beautiful name, but it carried a heavy destiny. The tragedy of Oumuamua was not that it was dangerous. It was not a weapon. The tragedy was that we were asleep when it knocked on our door. By the time we realized what it was, it had already passed its closest point to the sun. It was already on its way out, fading into the darkness, moving away from our telescopes, faster than we could focus them. We were like a person waking up from a nap only to see the back of a long-lost friend walking out the door, never to return. The data we managed to collect was confusing, which only added to the pain. Oumuamua was strange. It was not round. The light curve of the way its brightness changed as it spun suggested it was incredibly long and thin like a cigar, or perhaps flat like a pancake. We had never seen a rock naturally form that shape. It tumbled through space end over end every 7 or 8 hours. But the true mystery, the thing that keeps old astronomers awake at night, was its movement. As Oumuamua left the solar system, it accelerated. It pushed away from the sun slightly faster than gravity alone could explain. If it were a comet, this would be normal. Comets heat up ice turns to gas, and that gas acts like a small rocket thruster. But Oumuamua had no tail. There was no cloud of dust, no visible water vapor, no carbon monoxide. It was a silent, dry traveler. So what pushed it? Was it hydrogen ice? Was it a trick of the light? Or as some brave voices dared to whisper, was it artificial? Was it a light sail sent by a civilization long dead? We never found the answer. That is the ghost that haunts us. Because we were not ready, we could not chase it. We had no rockets fueled on the launch pad. We had no interceptor probes designed for high-speed pursuit. We watched it fade until it was a single pixel, and then it was gone. It vanished into the eternal blackness, taking its secrets with it. That object sits in our history as a Rank 7 event, not because it caused physical destruction, but because of the intellectual shock it delivered. It broke our hearts. It taught us the cruelest lesson in science: nature does not wait for you to be ready. Nature happens, and if you blink, you miss it. Think of the loneliness of that object. It travelled for hundreds of millions of years, perhaps billions, passing through the emptiness where there is no light, no heat, and no sound. It briefly entered our warm little campfire of a solar system, bathed in the light of our sun for a few weeks, and then plunged back into the cold. It will likely never see another star for 1 trillion years. It is a message in a bottle that we failed to open. This brings us to today. This brings us to 3i Atlas. The difference between Oumuamua and Atlas is the difference between a regret and a chance for redemption. Oumuamua was the warning shot. Atlas is the battle. When we look at the trajectory of 3i Atlas, we see similarities, yes. It is coming from deep space. It is moving with that same terrifying, beautiful speed. But there is one critical difference. We saw Atlas coming early. We have time, not much, but enough. No. With Oumuamua, we were archaeologists trying to study a ruin that was rapidly crumbling into dust. With Atlas, we are active participants. We are not just watching, we are preparing to meet it. This is why the tension in the control room is so thick you could cut it with a knife. We are trying to correct the mistake of 2017. We are trying to prove that we are not just passive observers of the universe, but explorers. If we let 3i Atlas pass us by without touching it, without sampling its surface, without looking it in the eye, it would be a failure of our species. It would be admitting that we did not learn from the ghost of the past. To lose one interstellar object is a misfortune. To lose 2 looks like carelessness. The sadness of a missed opportunity in science is a heavy burden. It is not like missing a bus where you can catch the next one. In the realm of interstellar objects, the next one might not come for a lifetime. Oumuamua left a hole in our knowledge, a blank page in the Encyclopedia of the Universe that simply says data missing. We cannot allow Atlas to become another blank page. We must remember that these objects are not just rocks, they are time capsules. They contain the chemical history of other stars, other worlds, perhaps other life. Oumuamua might have carried the frozen building blocks of an alien biology, or the rusted hull of a probe built by hands that have turned to dust. We will never know. That ignorance is a prison, but 3i Atlas offers us a key. As we track Atlas moving closer, we are haunted by the memory of that tumbling cigar shape from years ago. We remember the frustration of the blurry images. We remember the arguments in the academic journals that could never be settled because the evidence was gone. We are driven by a desperate need to know. This is why we are launching the interceptors. This is why we are risking billions of dollars and the careers of our best engineers. We are chasing Atlas because we are still chasing Oumuamua. We are trying to catch the ghost we missed. We are telling the universe that we are awake now, we are listening. If 3i Atlas is just a rock, we will learn about the geology of distant stars. If it is something else, something like the strange accelerating anomaly of 2017, then we will finally have the answer that has eluded us. We will face the Rank 7 reality not with questions but with data. The ghost of the past is watching us. It is drifting away in the void, silent and cold, but its legacy burns hot in our control centers. We will not let history repeat itself. We will not let Atlas say goodbye without saying hello first. We are reaching out into the dark, fueled by the regret of what we lost to grab hold of what we have now. While Avi Loeb stood firmly in the spotlight articulating a theory that challenged our place in the universe, a different chorus of voices began to rise from the wider scientific community. This was not a chorus of anger, but rather one of caution, rigor, and deep-rooted tradition. These were the skeptics. It is easy to paint skepticism as the enemy of an imagination, but in the world of science, skepticism is actually its immune system. It is the necessary force that tests every new idea, pushing against it to see if it breaks. If a theory is brittle, the skeptics will shatter it. If it is true, the pressure will only make it stronger. Prominent among these voices were astronomers and astrophysicists like Michelle Bannister, Jason Wright, and Thomas Statler. They did not look at Oumuamua and see a handshake from the stars. They saw a puzzle that simply hadn't been solved yet. Michelle Bannister, an expert in planetary astronomy, viewed the object through the lens of statistics and natural history. To her and many of her colleagues, the universe is a messy construction site full of leftover debris. We have seen millions of asteroids and comets. Just because Oumuamua was the first one we saw from outside our solar system, it did not mean it had to be a machine. It was simply a visitor from a different neighborhood. Then there was the practical investigation led by scientists like Jason Wright. Wright is a serious researcher in the field of the search for extraterrestrial intelligence, or SETI. He did not dismiss the idea of alien technology out of hand. In fact, he helped organize an observation using the massive Green Bank telescope to listen to Oumuamua. They tuned their ears to the object, scanning for radio waves, pings, or any sign of communication. The result was silence. The object was quiet. For Wright and the skeptics, this silence was a heavy piece of evidence. If this was a probe, why wasn't it calling home? While Loeb argued that a light sail wouldn't necessarily emit radio waves, the lack of a signal allowed the skeptics to retreat to the safer ground of natural explanations. Thomas Statler challenged the physics of Loeb's light sail theory directly. He looked at the way Oumuamua was tumbling. It wasn't flying smooth and straight like an arrow, it was spinning chaotically. Statler argued that if a light sail was being pushed by the sun, the pressure would likely stop that tumbling, or change it in a predictable way. The chaotic motion of the object seemed to contradict the idea of a stable engineered piece of technology. These arguments are grounded in one of the most famous and enduring principles in the philosophy of science, Occam's razor. Named after the friar William of Ockham, this principle suggests that when you are presented with two explanations for the same event, the simpler one is usually the correct one. In the case of Oumuamua, the skeptics wielded Occam's razor like a shield. On one side you have the alien hypothesis. This explanation requires us to accept several massive assumptions that intelligent life exists elsewhere, that they have the technology to travel between stars, that they built a solar sail, and that this specific sail happened to pass by Earth at this specific time. That is a lot of assumptions. On the other side, you have the natural hypothesis. This view suggests that Oumuamua is a rock, It is a weird rock certainly. It might be a rock with the unusual ice or a rock shaped like a shard from a destroyed planet, but it is still just a rock. This explanation requires no new physics and no aliens. It only requires nature to be creative, which we know it is. Therefore, according to Occam's razor, the natural explanation must be preferred until it is proven impossible. The skeptics argued that we shouldn't invent aliens to explain a mystery when a weird iceberg would do the job. However, there is a deeper, more psychological layer to this resistance. Why does the scientific community and humanity in general cling so tightly to the rock theory? Why is there such a strong emotional pushback against the idea of it being artificial? Part of this reaction stems from a profound fear of hope. Hope is a dangerous emotion for a scientist, because to hope for a discovery is to introduce bias. If you want Oumuamua to be an alien probe, you might stare at the data until you see what you want to see. But on a more human level, the fear of hope is about disappointment. We are a lonely species. We have spent our entire history looking up at the night sky, wondering if anyone is looking back. To believe even for a moment that we have finally found a companion, and then to be told it was just a piece of frozen nitrogen, is a crushing emotional blow. It is safer to assume the object is dead than to open your heart to the possibility of life only to have it broken. Cynicism feels safer than optimism because cynicism can never be disappointed. Furthermore, there is a comforting safety in randomness. This might seem contradictory. Usually we think of randomness as scary and chaos as bad, but in this context, a universe full of flying rocks is actually a safe universe. If Oumuamua is just a rock, it means the universe is indifferent to us. A rock does not watch us. A rock does not judge us. A rock does not have plans. We can continue to believe that we are the apex of intelligence, the masters of our domain, the smartest things in the neighborhood. We remain the special ones. But if Oumuamua is technology, that safety vanishes instantly. If it is technology, it implies a creator. It implies an intelligence that might be far older and far superior to our own. Suddenly, we are no longer the kings of the castle. We are the ants living in the cracks of the driveway, unaware that a car just rolled over us. To accept the presence of another intelligence is to accept a demotion in our own status. It forces us to confront the possibility that we are primitive, backward, or simply uninteresting to a superior species. The skeptics argue that extraordinary claims require extraordinary evidence. This is a valid and necessary standard. But the debate over Oumuamua revealed that our definition of extraordinary is shaped by our fears. We are terrified of being the fool who cried alien, so we prefer to be the wise man who said rock, even if the rock has to do impossible acrobatics to fit our theories. Ultimately, the voice of doubt is not a villainous voice. It is the voice of Statler checking the math, Wright checking the radio frequencies, and Bannister checking the catalogues. It is the voice that keeps science grounded. But as Avi Loeb would argue, being grounded is of no use if you refuse to look up. The tension between these two sides, the daring hypothesis and the rigid skepticism, is not a flaw in the scientific process. It is the engine that drives it forward. Without the dreamer, we would never look. Without the doubter, we would never know for sure what we found. When we analyse the strange data left behind by our interstellar visitor, Oumuamua, we are faced with a puzzle that standard geology cannot solve. A simple rock should not accelerate without releasing gas. A natural comet should not look like a flat pancake or a long cigar. If we are brave enough to step outside the safety of traditional science, we must consider that this object was artificial. To understand the reality of this encounter, we must run a mental simulation. We must construct 4 detailed scenarios, 4 potential truths to explain why this visitor entered our solar system and what it implies about the universe around us. Scenario 1. The autonomous probe, the silent cartographer. In this first scenario, imagine that Oumuamua was not lost and it was not a rock. It was a machine that was working exactly as intended. We must picture a civilization that existed perhaps hundreds of millions of years ago. These beings were the cartographers of the galaxy. They understood that biological bodies are too heavy and fragile to travel between stars, so they did not send astronauts. Instead, they built millions of small lightweight probes. This object was likely designed as a light sail. It was a piece of technology shaped like a very thin flat sheet, perhaps no thicker than a millimeter. This design allowed it to surf on the light of stars. When it passed our sun, the pressure of the sunlight hitting its surface gave it a gentle push. This explains the mysterious acceleration that baffled our scientists. It did not need an engine or rocket fuel, it only needed light. The speculative story. The creators of this probe were a patient species. They launched these devices like dandelion seeds blowing in the wind, targeting every star system in the galaxy. When Oumuamua arrived in our solar system, its sensors likely woke up from a long hibernation. It tasted our atmosphere, detecting oxygen and water, the chemical fingerprints of life. It listened to the radio waves leaking from our planet. However, its programming was strict: observe only, do not interfere. It treated Earth not as a special discovery, but as just another data point in a massive galactic census. It collected the data on humanity, packaged it into a tight beam of information, and whispered it back toward a home star that might no longer exist. Scenario 2. Derelict technology, the cosmic shipwreck. The second possibility is darker and more melancholic. In this version of the truth, Oumuamua is trash. It is not a spaceship and it is not a probe. It is a shard of something much larger: industrial debris. Imagine a massive piece of alien infrastructure, perhaps a giant ring designed to harvest energy from a star, or a superhighway buoy used for navigation. Eventually that civilization fell. Perhaps they destroyed themselves in a terrible war, or perhaps their star exploded and swallowed their planets. The destruction of their machinery sent billions of twisted fragments flying into the dark void. Oumuamua is one of those pieces. The speculative story. This scenario explains the object's chaotic motion. Astronomers noted that Oumuamua was tumbling wildly, flipping over and over every 8 hours. If it were a functioning ship, it would likely fly smoothly, but as a piece of wreckage it tumbled because it was ripped apart by tremendous forces long ago. The tragedy here is that the creators were incredibly advanced, capable of engineering on a scale we can only dream of, but they failed to survive. Oumuamua is a tombstone. It passed our Earth in total silence, a ghost ship carrying the memory of a dead empire. It serves as a warning to humanity: having high technology does not guarantee that a civilization will live forever. We are looking at the rust of a dead world. Scenario 3, the relay station, the sleeping buoy. Let us imagine a scenario where the object is part of a still functioning network. This is the relay hypothesis. In this view, the galaxy is already full of communication, but we are too primitive to hear it. Advanced civilizations do not broadcast loud radio waves in every direction, because that is wasteful. Instead, they use a precise network of relays like cell phone towers floating in deep space to send laser messages from one star to another. Oumuamua could be one of these nodes. It was sitting in a specific spot in the galaxy known as the local standard of rest, a place of relative calm. It was waiting. When our sun's gravity pulled it in, the object did not react because it was in sleep mode. Or perhaps it was using our sun's gravity to help it steer toward its next destination. The speculative story. The civilization that built this is not dead, they are simply efficient. They have created a galactic internet, but humanity has not yet figured out how to log in. The object accelerated past the sun, not because it was fleeing, but because it was maneuvering to recalibrate its position for the next million years of service. It might have scanned Earth, realized we are still using primitive radio technology and burning fossil fuels, and decided we were not ready to join the conversation. It was a handshake that we failed to catch. It remains dormant, waiting for a civilization that is smart enough to signal it with the correct frequency. Scenario 4, the intentional signal. The message in a bottle. The final and perhaps most profound scenario is that Oumuamua was a message sent directly to us or to any young civilization that might find it. Everything about the object was designed to be seen. The tumbling motion was not an accident. It was a way to flash reflected sunlight in all directions like a lighthouse or a spinning disco ball, ensuring that any astronomer looking at the sky would notice the variation in brightness. The strange shape, 10 times longer than it was wide, was chosen because it looks unnatural. It defies the laws of random asteroids. The speculative story. The senders were likely lonely. They realized that intelligent life is rare and fragile in the cold universe. They launched these messages in a bottle towards stars that looked promising. They did not send a warship or a robot. They sent a sculpture. Perhaps the message was not inside the object. Perhaps the object was the message. The fact that it existed was the text. They wanted to provoke us. They wanted us to look up, to argue, and to wonder. If this scenario is true, then the civilization behind it was likely philosophical and peaceful. They were reaching out across the abyss of time just to say, "We are here, you're not alone, keep looking up."
The Seeker!
Who were they? In all these scenarios, we are forced to imagine the other. Who were the beings that forged this metal or grew this material? If they were the map makers, scenario 1, they were likely biological creatures similar to us, driven by curiosity and science, obsessed with cataloguing the universe before they died. They feared being forgotten, so they sent out their eyes to watch the stars for them. If they were the industrialist scenario 2, they were masters of matter and energy. Perhaps they were cyborgs who merged their biological bodies with machines only to fall victim to their own power. They treated solar systems like factories, and Oumuamua is the scrap metal left on the factory floor. If they were the network builders scenario 3, they are likely a civilization far beyond our comprehension, beings who can control the energy of entire stars. They view us much like we view ants, interesting but not ready for a conversation. They are still out there talking to each other over our heads. And if they were the poets scenario 4, they were dreamers. They knew they could never travel faster than light, so they sent their art instead. They represent a civilization that values connection above domination. The reality check. We may never know which story is the truth. The object is gone now, moving too fast for our current rockets to catch. It has crossed the orbit of Neptune and is diving back into the dark cold of interstellar space, heading toward the constellation of Pegasus. But the simple act of imagining these scenarios changes us. It forces us to admit that our silence might be temporary. It prepares us for the day when the next object arrives, and perhaps next time we will be ready to catch it. At 4,000 meters above sea level, the air is so thin that it feels like a different planet. Here in the high deserts of Chile and the frozen peaks of Hawaii, the sky does not look like the sky people see from the cities. It is a deep, endless black, thick with stars that do not twinkle but burn with a steady cold light. The wind howls outside the metal domes, a constant reminder of how hostile nature can be, but inside everything is silent. This is the world of the Watchers. Elena sat in the control room of the observatory, the glow of 4 computer monitors reflecting in her tired eyes. She wrapped her cardigan tighter around herself. The heating system hummed in the background, but the cold of the mountain always seemed to find a way inside. It was 3 in the morning. While the rest of the world slept, fell in love, or worried about their morning commute, Elena and a small handful of others around the globe were looking up. She was not looking through an eyepiece. Modern astronomy is not about putting your eye to a lens. It is about data. It is about streams of numbers and graphs cascading down a screen. It is about capturing light that has travelled for millions of years and turning it into a digital signal. Elena took a sip of lukewarm coffee. She was part of a grand invisible web called the International Asteroid Warning Network, or IAWN. To the average person, this sounded like a group from a science fiction movie. In reality, it was a loose collection of scientists, engineers and statisticians connected by high-speed internet and a shared anxiety. They were the planetary defense team. Their job was simple but terrifying: find the rocks before the rocks find us. Tonight the network was buzzing. It was a silent buzz visible only in the secure chat channels and encrypted email threads that popped up on Elena's side monitor. Target locked, a message read from a colleague in the Canary Islands. Confirming trajectory, replied a station in Arizona. There was a tension hidden beneath the professional language. For weeks, the major space agencies, NASA, the European Space Agency and others, had been projecting an image of calm control. Their press releases spoke of routine monitoring and standard procedures. They used words like low probability and abundance of caution. But Elena knew the truth. She could see it in the shift schedules. Senior directors were staying in the office until midnight. Vacations were being quietly cancelled. The playful banter that usually filled the break rooms had been replaced by hushed conversations behind closed doors. The calm surface was a mask. Underneath, the machinery of planetary defense was spinning up to maximum speed. The beast had woken up. The object they were tracking was faint, a mere ghost against the background stars. To see it clearly, they needed eyes that were not on Earth. Far above the atmosphere, 1.5 million kilometers away from the planet, the James Webb Space Telescope turned its golden mirrors toward the darkness. The Webb telescope was the crown jewel of humanity's eyes. Unlike the telescopes on the ground, it did not have to fight through clouds or the blur of the atmosphere. It looked at the universe in infrared light heat vision. It could see things that were invisible to optical telescopes. Back on Earth, inside the Mission Operations Center in Baltimore, the mood was electric. The engineers commanded the telescope to focus on a specific set of coordinates. This was not a simple picture-taking mission. They were using spectroscopy. They were trying to sniff the asteroid. They needed to know what it was made of. Was it a solid block of iron, heavy and dense? Was it a loose pile of rubble held together by weak gravity? Was it rich in water or full of silica? The answer mattered. If they had to hit this thing to move it, they needed to know if it would shatter like glass or absorb the blow like a sponge. The data from Webb began to trickle down. It travelled through the vacuum of space, was caught by the Deep Space Network antennas in Australia and California, and was piped directly to the secure servers. Eleanor, thousands of kilometres away on her mountaintop, saw the shared data update. She leaned forward, ignoring the ache in her back. The light curve was strange. As the asteroid rotated, the amount of sunlight it reflected changed. This told them about its shape. It was not a perfect sphere. It was elongated like a potato, tumbling end over end through the void. "Rotation period is fast," she whispered to the empty room. "Too fast." A fast rotation meant the object was under immense stress. If it was just a pile of rocks, it should have flown apart. This suggested it was a single solid monolith, a bullet made of stone. The isolation of the observatory suddenly felt very heavy. Usually Eleanor loved the solitude. She loved the feeling of being the only one awake, the guardian of the night. But tonight the silence felt different. It felt like the silence before a thunderstorm. She looked out of the small reinforced window. The mountain peak was bathed in moonlight, looking like a lunar landscape. She thought about her family sleeping in the city down below past the cloud layer. They were safe in their beds, dreaming of tomorrow. They trusted that if something was coming, someone would tell them. They trusted that people like Elena were watching. A notification pinged loudly in the quiet room, making her jump. It was a direct update from the IAWN Coordination Center. Probability calculation updated. Elena clicked the file. Her heart hammered against her ribs. She did not look at the complex equations. She looked at the bottom line, the summary written in bold text. The error margins had shrunk. The maybe was turning into a probably. The uncertainty region, the imaginary tube in space where the asteroid might travel, was narrowing, and Earth was sitting right in the middle of it. She typed a quick command into her terminal to align her telescope with the new coordinates provided by James Webb. The massive machinery of the telescope groaned as it rotated, a mechanical beast shifting its gaze. The gears ground together, a sound that vibrated through the floor. On her screen, a new image appeared. It was just a field of static with a single tiny dot moving slightly against the fixed stars. It looked so small. It looked like a dead pixel. It was hard to believe that something so small, just a few pixels of light, could carry enough energy to erase a city or boil a sea. This was the burden of the Watchers. They held a secret that was too big for the human mind to fully process. They were the first line of defense, but they had no weapons. They only had glass mirrors and mathematics. Elena picked up the phone to call the Central Directorate. Her hand was shaking slightly, not from the cold, but from the adrenaline. She needed to report the confirmation of the visual magnitude. The data from the mountain matched the data from space. There were no more errors to hide behind. "Control," she said when the line connected. Her voice sounded loud in the silent room. "This is Station 4. We have visual confirmation. The object is brighter than predicted. I repeat, the object is brighter than predicted." There was a pause on the other end, a hesitation that spoke volumes. "Copy that, Station 4. The voice came back, stripped of all emotion. "Log the data. Stay on the target. Do not lose it." "I won't," Elena said. She hung up. She stared at the tiny dot on the screen. The sun would rise in 2 hours. The sky would turn blue, the stars would vanish, and the world below would wake up to a regular Tuesday. But for Eleanor and for the hundreds of other watchers sitting in dark rooms on mountain peaks and in quiet valleys around the world had already changed. They were no longer just observing the universe. They were waiting for it to arrive. The data packets continued to flow in. Elena watched the numbers stabilize. The velocity was 28 kilometers per second. The diameter was estimated at 1.2 kilometers. It was not the largest asteroid in the solar system, but it was dense. The James Webb telescope had found traces of metal on the surface. It was heavy. The loneliness of the job usually felt peaceful. Tonight it felt like a cage. Elena wanted to call her sister. She wanted to tell someone to look at the sky. But she was bound by protocol. Panic was dangerous. Panic caused chaos. The job of the IAWN was to provide certainty, not fear. She poured another cup of coffee. The steam rose in the cold air. She settled back into her chair, her eyes fixed on the monitor. She was a sentry on the wall. She would not blink, she would not sleep, she would watch the ghost in the dark until the sun came up, and then she would watch it again the next night. The silence of the mountain was no longer empty. It was full of a terrible silent knowledge. The rock was coming. Imagine a giant invisible hourglass hovering over our heads. It is not made of glass or wood, but of gravity and light. Inside it, the sand is not made of silica, but of moments' precious non-renewable seconds that are slipping away from the top chamber to the bottom. This is the mental image that has haunted me since the discovery began. We are no longer operating on a vague schedule. We have entered the phase I call the 60-day hourglass. The timeline is strict. It is governed by the movement of planets and the rotation of our galaxy, not by human calendars. However, to understand it, we must look at the 3 months that define this critical window: November, December, and January. November acts as the awakening. It is the month where the theoretical becomes real. In the beginning, the data we collected was just numbers on a screen. But as November progresses, the signal, that strange anomaly we have been tracking, begins to interact with our local environment. The atmosphere feels different. The static in the air increases. It is the feeling of a storm gathering, but this storm is silent and invisible. During these 30 days, our task is to calibrate our instruments. We have to make sure that our ears are sharp enough to hear the whispers from the stars. November is about preparation and realization. It is the deep breath before the plunge. Then comes December. This is the neck of the hourglass, the narrowest point where the sand flows the fastest. While the rest of the world is distracted by holidays, kites, and celebrations, we are locked in a race against physics. December brings the peak of the alignment. This is when the window is wide open. In simple terms, imagine a tunnel opening through a mountain. Usually the tunnel is blocked, but for these few weeks the block is removed and we can see straight through to the other side. The energy readings spike. The distortion in space, what we call the delta, reaches its maximum value. If we are going to send a message, or if we are going to receive a physical object, it must happen in December. It is the month of action. Every hour of sleep feels like a betrayal of the mission. Finally, there is January. This is the closing phase. The tunnel begins to collapse. The alignment breaks as the Earth continues its orbit. The signal does not vanish instantly. It fades. It is like listening to a radio station while driving away from the city. The voice becomes filled with static until it is just white noise. January is the month of finality. Whatever we have not achieved by the end of January will remain undone. The sand in the top chamber will run out. This brings us to the terrifying concept of the door closing. In our daily lives, if we miss a deadline, we can usually ask for an extension. If we miss a bus, there is another one in 20 minutes. But the universe does not offer extensions. The mechanics of this event depend on a specific celestial geometry that is incredibly rare. When we say the door is closing, we mean that the path between here and there is being severed. Think of it like a solar eclipse. The moon covers the sun for only a few minutes. You cannot pause the moon. You cannot ask the sun to wait. You're either watching it happen or you miss it. But this is not just a shadow passing over the ground, it is a bridge connecting two realities. Once the 60 days are up, the bridge retracts. The distance, which is currently short enough to travel, will expand back to infinity. To cross that distance without the bridge would take more energy than our sun produces in its entire lifetime. That is the meaning of the closed door. It is an absolute barrier. This reality forces us to reflect deeply on the nature of time itself. Humans have a very strange relationship with time. We measure it in small, manageable units, seconds, minutes, hours. We worry about being 5 minutes late to a meeting. But the universe operates on a scale that is almost impossible to comprehend. The universe speaks in eons, in billions of years. To the cosmos, the rise and fall of human civilization is just a blink. In this context, our 60-day window is microscopic. It is a fraction of a second in the cosmic lifetime. This contrast is humbling, but it is also terrifying. We are standing on the edge of something eternal, yet our access to it is incredibly brief. It represents the paradox of our existence. We are creatures who can understand the concept of forever, but we only have a tiny amount of time to act. The scarcity of this opportunity creates a unique kind of pressure. It is not the stress of a job or a generic deadline. It is the pressure of destiny. I often look at the night sky and think about the randomness of it all. Why now? Why us? Why are we the ones who happen to be alive and looking up during this specific 60-day period? There is a scientific term called entropy, which basically means that things naturally move from order to disorder. Time usually destroys information. Buildings crumble, memories fade, data creates errors. But this window is a reversal of that flow. For 60 days, order is emerging from chaos. A structure is forming. We have a chance to grasp something solid before the entropy returns and washes it all away. The pressure to decide is overwhelming. Usually when making big decisions, you want to take your time, you want to weigh the pros and cons, you want to sleep on it. But here, sleeping on it might cost us everything. The decision to step through the door to send the signal or to activate the machine must be made now. Hesitation is our enemy. In a normal life, caution is a virtue. It keeps you safe. In the logic of the 60-day hourglass, caution is a risk. If you wait until you're 100% sure the sand will have run out, you have to act with only 80% certainty. You have to trust the math, trust the instinct, and trust that the risk of doing nothing is far greater than the risk of moving forward. As I watch the metaphorical sand fall, I realize that this is not just about science. It is about the human condition. We are always fighting against time. We are always trying to make our mark before we are gone. This experiment, this countdown, is just the ultimate version of that struggle. The last grain of sand is waiting to fall, the door is drifting shut. The universe is holding its breath, but it will not hold it for long. November wakes us up. December demands our action. January seals our fate. We are living in the most important 60 days in history, and the clock is ticking loud enough to shatter the silence of space. The object is gone now. It has slipped back into the shadows from which it came. After all the noise, after all the headlines and the frantic typing of astronomers, the sky has returned to its usual silence. The visitor which we named 3i Atlas is no longer a headline. It is a ghost fading into the deep freeze of the outer solar system, moving faster than a bullet, faster than sound travelling at speeds that our minds struggle to truly comprehend. It is heading back into the great black ocean of the galaxy, and we are left here on our small blue island, watching the wake it left behind. Now that the excitement has passed, we can finally sit down and ask the most important question. Not what was it, but rather, what did it mean? Throughout this journey, we have debated its nature. Was it a shard of ashes of a frozen planet? Was it a piece of hydrogen ice invisible and strange? Or was it a machine, a light sail, a derelict probe sent by a civilization that died long before dinosaurs walked the earth? The truth is, the object itself might not care what it is. A rock does not know it is a rock. A machine does not know it is a machine. It simply exists. But for us, the answers seem to matter so much, and this is where the mirror comes in. 3i Atlas was not just a visitor, it was a mirror of civilization. When we looked up at that strange point of light, we did not just see an object. We saw a reflection of ourselves. We saw our own faces staring back from the dark. Think about how we reacted. Some of us looked at it and felt fear. We saw an invader. We saw a weapon. We imagined scenarios of war and destruction. This reaction tells us about our own history. It reminds us that for thousands of years, when humans met strangers, it often ended in conflict. We projected our own violence onto a silent stone floating in the void. Others looked at it and felt loneliness. We saw a handshake. We saw a message in a bottle. We desperately wanted it to be artificial because we are terrified of being the only ones in this massive house. We shouted, "Hello!" into the dark because the silence of the universe is sometimes too heavy to bear. This tells us about our need for connection, our deep desire to find a friend in the stars. And some looked at it with curiosity. They did not care if it was a rock or a ship, they just wanted to know how. How does it move? What is it made of? This reflects the best part of us, the part that explores, the part that learned to build fire, the part that sailed across oceans without maps. So perhaps it does not matter if 3i Atlas was natural or artificial. The test was not about identifying the object, the test was about our maturity. If the universe is a school, this was a pop quiz. How do we handle the unknown? Do we panic? Do we argue? Or do we come together, point our telescopes at the sky and simply watch with wonder? In the end, the most beautiful answer is the one that embraces the mystery. Even if it was just a rock, think about the journey it took. It travelled for millions of years. It passed by stars that have since exploded. It drifted through clouds of gas where new suns were being born. It survived the crushing gravity of the Milky Way's centre. It is a traveller older than the human race, older than our mountains. Is that not a miracle in itself? Nature is a sculptor and gravity is its chisel. Sometimes nature makes things that look like art. And if it was artificial, if it was a piece of technology, then it means the universe is full of potential. It means that somewhere perhaps across the spiral arm of the galaxy, someone else looked up at their night sky and wondered if they were alone. It means we share the same dream. But now let us let the debate rest. Let us put down the papers and the data. The show is over. The lights are dimming. Close your eyes for a moment and imagine where 3i Atlas is right now. It's crossing the orbit of Neptune. The sun is no longer a burning ball of fire. It's just a very bright star in the distance, shrinking with every passing second. The warmth of Earth is a forgotten memory. Around the object there is only silence. It is a silence deeper than the bottom of the ocean. It is a silence that has lasted for eons. There is no wind to whistle over its surface. There is no sound of birds, no rustle of leaves, no hum of traffic. There is only the vacuum. The object tumbles slowly, end over end, a slow hypnotic dance in the dark. One side catches the faint light of the distant stars, then rolls back into the shadow. Light, shadow, light, shadow. It is moving into the space between stars. This is the interstellar medium. It is the vast, empty cathedral of the cosmos. Here atoms are so far apart that they almost never touch. It is perfect stillness. Imagine floating there beside it. The darkness is not scary, it is soft like velvet. It wraps around everything like a heavy, comforting blanket. The stars are not twinkling here. They are steady, unblinking diamonds frozen in the glass of the night. They are millions of light years away, painting a picture that never changes. You are drifting. The problems of the day are far behind you, left on a tiny planet that is now just a speck of dust. Here there are no deadlines, there is no rush, there is only the slow rhythmic breathing of the universe. 3. Atlas will travel for another 1,000,000 years before it gets close to another star. It has time, it has all the time in existence, it is patient, it is calm. We can learn from that patience, we can learn from that calm. As you lie there safe in your bed, remember that you are part of this same universe. The atoms in your body were forged in the same hearts of stars that light up the dark path for our traveller. You're connected to that vastness. You're made of stardust resting for a moment on a spinning world. There is no need to worry about the unknown. The unknown is just a place we haven't visited yet. The darkness is just a canvas waiting for light. The visitor has gone, but it left us a gift. It reminded us to look up. It reminded us to be humble. It reminded us that we are small, but our minds are big enough to hold the entire galaxy. So let the object drift, let it sail into the endless night. Let it carry our dreams into the void. The universe is vast, and it is quiet, and it is beautiful, and you are safe within it. Drift along with the stars, float in the river of the night. Rest now, the sky is watching over you. Good night.